So before moving on to the CMIP6 projections, I wanted to introduce this paper which looked specifically at convective parameterizations and their impact on extremes over the Indian region. It's a nice paper which uses a regional model at sufficiently high resolution and changes the convective parameterizations and looks at the impact on these various parameters. R95, so total rainfall when exceeding 95th percentile, 99th percentile. RF10 is when total rainfall exceeds 10th percentile, 20th percentile. Consecutive dry days when precipitation is less than a millimeter. Consecutive wet days, number of days when precipitation is greater than 10 millimeter, number of days when the precipitation is greater than 20 millimeter. This is kind of a good range of variables to explore to understand better which parameterization does well and why. Of course, this analysis is not complete all in one paper, but one can use these outputs to carry the analysis forward, as I will show later on. For example, moisture budget calculations can be done to see how each convective parameterization interacts with the dynamics and thermodynamics. The convective parameterizations, I won't go into the details of what the differences are, but there are names: Grell, Ken and Fritz, modified schemes. This is Tiedtke. The IMD data is used: MIT, MLGO, GLMO. So these are various parameterization schemes. I can point you to the acronyms, but you can look it up in the paper. I don't want to get distracted by those, but basically, let's say some of them will be based on data from mid-latitude land where convection may be not elevated, whereas some may be based on tropical data where the convection is elevated from the surface, and so on. So all kinds of differences are there between them in terms of how they represent conversion of convective available potential energy into vertical motion, convective inhibition, microphysics, dynamics, all kinds of combinations happen. I should be careful using those words because they mean different things for actual modelers, but you know that convection is a local process, especially in the tropics, where vertical motion and latent diabatic heating is going to create positive feedback and affect the whole dynamic, thermodynamic and microphysics altogether. So start by looking at the June, July, August mean R10. So this is the number of days where rainfall is greater than 10 millimeters per day over the period of 2000 to 2005. So IMD data shows this distribution, and IMD's rain gauge coverage is pretty good, one of the best data sets in the world as far as rainfall is concerned, despite all the uncertainties that may be there in terms of reporting and so on and so forth. And you can see the impact of the Western Ghats here, the Himalayan foothills, the northeast region, and the core monsoon zone. So the Himalayan foothills here and the core monsoon zone. And the main thing you would see is that some are doing the Western Ghats fairly well, like this one and this one, even though the distribution is not exact in terms of either the orographic representation or the distribution in width on the western versus eastern side of the Ghats maybe, and so on. So the coarse resolution models have problems with orography. This model is regional model with higher resolution, but still it's not high enough to capture those kind of topographies. Plus the regional models at high resolution tend to produce excess orographic rainfall, but that again depends obviously on the convection scheme. As you can see, this one is producing high and this one is producing extremely high rainfall. Here is the scale going from millimeters, so this is 50 millimeters to 4, sorry, days are 10 days, so 50 days to 400 days. So it's producing lots of days here. Okay, so wider distribution and lots of days, whereas the others are not producing the Western Ghats at all. Okay, so this one is doing the southern part but not the northern part. This is barely capturing anything at all, and so on. And almost all of them are missing the core monsoon zone here. Look at the number of days here. This is in the range of, let's say, the colors are going from 200 to, let's say, maybe 250 days. Most of these are less than 100 days. This one may be capturing closer to IMD than the rest of them. But this is the so-called dry bias over land, where most models tend to produce less rain over the seasonal total compared to observations, and that is manifest here as number of days with rainfall greater than 10 millimeter per day. Okay, moving on to R20, where number of days is greater. Number of days with greater than 20 millimeter per day of rainfall, same period, again IMD data, and you can see that this is magically getting better for 20 days. It still has too many days of high rainfall here, but it's still missing the Himalayan foothills. This one is not doing well at all, even though it's gotten a little bit better. Little bit better here. This also got a little bit better here, but still missing this massive amount of rain. But they are doing better now in the north east compared to their performance here, which is also better, for example, than this. So this is doing this better, but not so much this. This is doing this and this somewhat better, missing this one but doing this, and these are doing these but not here, and so on. So these, each one of them, why do we look at these separately? Because each one points to a kind of convection dynamics they are capturing and missing. This is a straightforward orographic rainfall with southwesterly jet running into the Western Ghats, whereas here there's a combination of the orographic rain as well as the circulation that is feeding the moisture from the Bay of Bengal versus directly from the southwesterly jet. Okay, so it may be an issue of how the convection is taking the background moisture and creating rainfall. Okay, so those kinds of details tend to get analyzed when you read the paper, so you can look at those. I'm just trying to give you a sense that convective parameterization can produce all kinds of biases in model simulations of rainfall ranges. Looking into the extremes here, R95, so 95th percentile in millimeter per day for all convective parameterization schemes and IMD during the same period. So the IMD data for this period is showing what we called before as widespread extremes. So 95th percentile has precipitation in the range of these millimeters per day, going all the way to 70 over the Western Ghats, and in the range of 40 to 50 in the Himalayan region northeast, and here it's remaining in 30 to 40 millimeters per day. Grell maybe overdoing it a little bit in terms of rain rates, but the distribution is not bad, but the Himalayan foothills are completely missing here again. This is doing much more over peninsular India, which is completely opposite of what IMD says, and this is I don't know, you can just look at these. MIT parameterization is completely missing almost everything, so it didn't do well at all. Cambridge again. So you can see that one can diagnose the processes that are working. This could be related to, again, as I said, orographic performance of the convective parameterization, elevated versus surface-based convection, which is tropical versus extratropical convection, and so on and so forth. So people often do what are called ensemble physics, so they tend to mix the parameterizations with some kind of a weighting to see if this captures the Western Ghats better and this captures the Himalayan foothills better and the core monsoon zone better, then can you mix the two and get overall better performance. Okay, these are consecutive dry days, so for all cumulative convective parameterization schemes and IST. So this is here is the IMD baseline, has high number of consecutive dry days here, and of course in the desert region of the Western Indian subcontinent, as well as the core monsoon zone and the peninsular India. So you can see this distribution, whereas the wetter regions have fewer consecutive dry days, whereas this one is producing. Now it didn't do so well in the extremes and the moderate rainfall amounts, which obviously means it's producing too many dry days. This has got a combination, so it didn't do so well here, so it's producing too many dry days compared to IMD here, for example. This one is doing the Western Ghats better and the Himalayan foothills better. Maybe it's doing overall better than others. Again, MIT, which didn't do so well in the rain, is now doing extremely poorly in the consecutive dry days. So you have to look for dynamic consistency in terms of how rainfall duration, frequency, and intensity is happening, and how that also manifests in consecutive dry days and so on. And then diagnose the interaction with the large-scale circulation, the dynamics and thermodynamics. Okay, so the boundary conditions prescribed for the regional model are from the same source, so you expect the large-scale circulation and the moisture supply is common for all of those, and then convective parameterizations are taking that information and producing very different rainfalls in the lower bins of 10 millimeter per day, 20 millimeter per day, and 95th percentile. So this is just to give you a sense that when we look at historic performances, we can easily go after biases, uncertainties, and dependence on convective parameterizations, dynamic and thermodynamic responses, and precipitation efficiencies in terms of the warming and so on. But these have to somehow be carried forward to projections. So when we look, go and look now at CMIP6 projections, you have to remember that the models that are used have a range of convective parameterizations, and they are ensembled together, but each of them has these kind of details hidden in them in terms of their sensitivity to precipitation, mean precipitation and radiative balances, as well as extremes and the rainfall efficiency, vertical motion or dynamic response, saturation vapor pressure, and thermodynamic response. Okay, so these are necessary evils we have to deal with, and use the projections with some strategy in terms of how to plan for the future of precipitation changes and extreme changes. Okay.